Welcome to our latest video on the topic of optical isomerism. This video is suitable for A-level students. By the end of this video lesson, you should be aware that optical isomerism is a type of stereoisomerism that occurs when molecules contain an asymmetric carbon atom, i.e. a carbon atom bonded to 4 different groups. You should also understand that the presence of this asymmetric carbon atom, chiral center, leads to the existence of a pair of optical isomers called enantiomers that rotate plane polarized light in opposite directions. And finally, you should be able to identify chiral centers, explain the meaning of the term racemic mixture, and be able to draw pairs of optical isomers in mirror image forms. In our previous videos on isomers, we've learnt that isomers are groups of compounds that have the same molecular formula but a different arrangement of atoms. And we've also learnt that the molecular formula simply tells you the number of each type of atom present. In our previous videos, we learnt there are 2 main types of isomers, structural isomers and stereoisomers. And our first video described in detail the different types of structural isomers, i.e. chain, positional and series. Our second video on the topic of isomers looked at stereoisomers, and we learnt that stereoisomers have the same molecular formula and the same structural formula. In other words, they have the same bonds between the same atoms. However, these atoms are arranged differently in space. Now, in our first video on stereoisomerism, we looked in detail at E and Z isomerism. Now, in this video, we're going to focus on the second type of stereoisomerism, that is optical isomerism. To help us understand the difference between E and Z isomerism and optical isomerism, it's important to recap the main features of E and Z isomerism. Now, E and Z isomerism occurs in alkenes, and to have this form of isomerism, the alkene must have different groups on each carbon. So if we look at butene, we have a CH3 and a H on the one carbon, and a CH3 and a H on the other carbon. They're different. We've got a CH3 and a H. If we had 2 H's on one carbon, it wouldn't be able to exhibit this form of isomerism. The groups have to be different. And if you have butene, there's 2 possible arrangements that can exist. We could have the CH3 groups opposite each other, or we could have them on the same side of a carbon-carbon double bond. Now, when the CH3 groups are opposite each other in butene, that is called the E isomer. And it's called the E isomer because the German word for opposite starts with the letter E. Now, if the CH3 groups are on the same side of the carbon-carbon double bond, this version is called the Z isomer. And this is because the German word, which means together, starts with the letter Z. Now, the reason you can have different versions, different isomers of butene, is because of the double bond. The double bond locks the groups into different positions because the groups that are attached to the carbons, the H and the CH3s, can't rotate around the double bond because they're locked in place, because the double bond hinders the rotation of groups. Now, in our previous video, we learnt that geometric or E and Z isomers have very different physical properties. Their boiling points, melting points, solubilities will be different due to the fact that they have different bond angles and different shapes. When molecules have different shapes, they fit together differently, and therefore different amounts of energy would be needed to pull the molecules apart. That's why they have different boiling points and melting points. Now, if you have E and Z isomers and they have different physical properties, it means that it's very easy to separate E and Z isomers from each other in a mixture using techniques such as distillation. Now, we also discussed in our previous video that because E and Z isomers will contain the same functional groups, they will have similar chemical reactions, chemical properties. However, there are differences in the reactivity of these geometric isomers due to the fact that their bond angles are different. So now we're going to look at the second type of stereoisomerism, and that is optical isomerism. Now, optical isomerism occurs because of a lack of symmetry in molecules. And the simplest example of this is when you have 4 different groups attached to a carbon atom. Now, the carbon atom attached to 4 different groups is classed as a chiral center. Chiral means lack of symmetry, and this carbon atom is said to be asymmetric. Now, the presence of a chiral center, a carbon next to 4 different groups, leads to the existence of a pair of optical isomers. These are called enantiomers. Now, these enantiomers, or optical isomers, are non-identical mirror images of each other. We say they're non-identical because they cannot be superimposed one on top of the other. Now, a pair of optical isomers will have almost identical properties, apart from the fact that they rotate the plane of polarized light in opposite directions. Now, examples of molecules that have chiral centers and therefore exists as pairs of enantiomers are amino acids. Now, an example of amino acid is shown here in this picture, and you can see that the carbon in alanine has 4 different groups on it. It has a carboxylic acid group, COOH, a hydrogen atom, an amino group and an H2 group, and a CH3 group. And therefore, because of this, there is another form of alanine, a mirror image, and this mirror image is non-identical. They are non-identical mirror images because when you try to superimpose them one on top of the other, I cannot get all 4 colours here lined up. I can get 2 lined up, blue and green, but I can't get all 4 because they cannot be superimposed one on top of the other. That's why they're non-identical. Now, when drawing out pairs of enantiomers, you should draw them in the following form. The dotted line represents the mirror, and I've drawn 2 tetrahedrals to represent each isomer. Now, remember that a wedge or a triangle means that the bond is coming out of the board, and the dashed line means it's going behind the board, and the 2 other lines are in the plane of the board. And notice here we have mirror images of each other, and I'm marking in the chiral center. So if you're asked to draw pairs of optical isomers, you need to draw them in this form. Now, as I've said previously, optical isomers will have identical properties apart from the fact that they rotate the plane of polarized light in opposite directions. Now, light consists of waves which vibrate in all directions, but if light is passed through a polarizing filter, the light that emerges is vibrating in one direction or one plane only. That's what we mean by plane polarized light. Now, if a solution of an optical isomer or enantiomer is placed in the beam of plane polarized light, the beam is rotated either to the left or to the right, and a polarimeter is used to measure the amount of rotation or the angle of rotation. Now, an enantiomer can rotate the plane of polarized light either to the right or the left. And if we have an enantiomer that rotates plane polarized light to the right, we say it's the plus form. Now, a way of remembering this is if you're right about something, you're positive about something. And if it rotates the light to the left, it's the minus form. Now, it's important to mention that if you have equimolar amounts of each optical isomer or enantiomer in solution, no overall rotation occurs because the rotation effects cancel each other out. And an equimolar mixture is called a racemic mixture. So now we're going to look to see if we can identify chiral centers. So I've drawn a molecule here with C2H5 attached to a carbon, which has an OH group, a fluorine, and a CH3 on it. So this carbon, the third carbon along, is a chiral center because it's got 4 different groups attached. So I'm going to mark it with an asterisk, and this is my chiral center. And because I've got one chiral center, a pair of enantiomers, a pair of optical isomers, will exist. Now this is how I would represent the mirror image forms of each other, the 2 optical isomers that exist because of the chiral center. And one optical isomer would rotate light to the right, and I'd call that the plus form, and one to the left, and that would be the minus form. So here's a second example of a molecule with a chiral center. So I'm looking for a carbon next to 4 different groups. So I'm going to mark this carbon with an asterisk, and I'm just going to circle the group so I know what the 4 different groups are and to double check that they're different. And because it's got one chiral center, there will be a pair of optical isomers for that molecule. So if I want to draw those optical isomers and show that they are mirror images of each other, I would draw them in the following form. So this is how I would draw the 2 enantiomers. Now I draw them in tetrahedral forms. I mark in the chiral center, and the dashed line represents the mirror, and one of the enantiomers would rotate plane polarized light to the right, that would be the plus form, and one to the left, that would be the minus form. Now it's very common for molecules to have more than one chiral center in it. So I'm going to look at this molecule here that I've drawn, and I'm going to mark in the chiral centers, the carbons that have 4 different groups attached. So the first carbon has 4 different groups attached, and I'm looking for any other carbons that have 4 different groups attached. So this second carbon has 4 different groups attached, so I'm going to just mark that in with an asterisk as well. And I'm looking at the other carbons, and they don't have 4 different groups attached because the other carbons have 2 hydrogen on each of them. So there are 2 chiral centers in this molecule, which means there's going to be 2 pairs of optical isomers. Now, because optical isomers have virtually the same properties, apart from their ability to rotate plane polarized light, separating a mixture of optical isomers can be difficult. So therefore, chemists look to avoid having chiral centers, because if they have too many chiral centers, it means lots of pairs of isomers, and it's difficult to separate them. Now, many medicines are organic molecules that contain chiral centers. Now, one example is ibuprofen, which contains a chiral center and therefore exists as a pair of enantiomers. Now, as enantiomers can be difficult and expensive to separate from each other because they have identical properties due to their molecules having the same shapes and bond angles, ibuprofen, like many medicines, is sold to customers as a racemic mixture, an equimolar mixture of both enantiomers. Now, biological systems can often respond differently to one enantiomer compared to another, and there's always a risk that the unwanted form of a medicine could cause side effects. Now, ibuprofen has a pair of enantiomers, and one of the enantiomers is more biologically active than the other. However, the inactive isomer is converted to the more active one by an enzyme in the body. Now, if one of the optical isomers in a pair of optical isomers causes side effects when it's used as a medicine, it's very important that a patient is given the correct optical isomer. Otherwise, serious harm could happen to that patient. So we're now going to test your understanding of what we discussed in this video with some practice questions. So here's our first practice question. We want you to read through the question, pause the video, have a go at it, and then we'll go for the answers. So this first question is asking you to state which of the following compounds exhibit optical isomers, and it's asking you to label any chiral centers in the structural formulae with an asterisk. So if we look at compound A, there are no carbons there that are attached to 4 different groups, so that has no optical isomers. Compound B, we have 2 carbons in that molecule, the second one and the fourth one, that has 4 different groups attached. So there are 2 chiral centers, so that does have optical isomers. Compound C has 1 carbon next to 4 different groups. It has 1 chiral center, so that does have optical isomers. And compound D also has 1 chiral center, and therefore this will have optical isomers. So here's our second practice question for you to have a go at. Read through the question, pause the video, have a go at the question, and then we'll go for the answers. So now let's go for the answers to question 2. So the first part of the question is asking you to indicate a chiral center in this molecule by labeling it with an asterisk. So the chiral center is the carbon next to 4 different groups, and the carbon in this molecule that is a chiral center is labeled here on this slide. It's the carbon next to the benzene ring on the right hand side of the benzene ring, and that's the chiral center, so there's 1 mark for that. And then it says state how the optical isomers of salbutamol could be distinguished from each other. Well, the isomers would rotate the plane of polarized light in opposite directions, 1 mark for that. And the last question says, suggest a reason why only 1 optical isomer of salbutamol is used as a pharmaceutical. So the reason would be side effects from the other optical isomer, 1 mark for that. So here's question 3. Now this comes in 2 parts, part A and part B, and this first slide has part A. So read through the question, pause the video, have a go at part A, and then we'll have a look at part B. So here's part B. Once again, read through the question, pause the video, have a go at it, and then we'll go for the answers to parts A and B. So now let's go through part 3A. So part 3A is asking you to indicate the position of any chiral center. So the chiral center is on carbon 2 here, and I've marked it in with an asterisk. And it's a chiral center because it's a carbon next to 4 different groups. There's 1 mark for correctly identifying the chiral center. So here's the answers to 3B, parts 1 and 2. So part 1 is asking you to define the term racemic mixture. Well, this is an equimolar mixture of 2 enantiomers, or optical isomers. 1 mark for that. And it says state the effect, if any, that a racemic mixture has on the plane of polarized light. Well, a racemic mixture would have no effect on the plane of polarized light, because the one enantiomer would rotate light to the left, the other would rotate it to the right. Because you've got an equal molar of both, that cancel each other out, the rotating effects cancel each other out, and therefore you see no effect on the plane of polarized light. There's 1 mark for that. So here's question 4, which is our final question for you to have a go at. And the question is asking you to draw the 2 mirror image forms of the compound 1-bromo, 1,2-difluoroethane. Pause the video, have a go at the question, and then we'll go for the answers. Now to answer this question, I just need to draw 2 tetrahedrals and I need to identify the 4 groups that are attached to the carbon. So you can see I've got a fluorine, I've got a hydrogen, I've got a bromine, and I've got a CH2F. So I need to put those on the tetrahedral. I can put them anywhere, and then I need to draw another tetrahedral that's a mirror image of it. So you can see I've lined up the H and the F on the left hand side, and I've lined it up as a mirror image, the H and the F on the right hand side of the mirror. Now if you draw 2 tetrahedrals, a mirror between them with a dotted line, and they're lined up as mirror images, and you've got the correct 4 groups on the carbon, so in other words the bromine, the CH2F, the fluorine and the hydrogen, you get 1 mark for that. So that concludes this video lesson. So after watching this video, you should now be aware that optical isomerism is a type of stereoisomerism that occurs when molecules contain an asymmetric carbon, i.e. a carbon atom bonded to 4 different groups. You should also understand that the presence of this asymmetric carbon atom, which is called a chiral center, leads to the existence of a pair of optical isomers called enantiomers that rotate plane polarized light in opposite directions. And finally, you should be able to identify chiral centers, explain the meaning of the term racemic mixture, and be able to draw pairs of optical isomers in mirror image forms. So that concludes our video. Please check out our YouTube channel, Dr. O Chemistry, and our Twitter site, which contains lots of chemistry information and links, @RadaChemistry.